Okay guys, in this video we're going to be talking about cell potentials for voltaic cells. And so we'll learn how to calculate the standard cell potential for a given redox reaction. And then we'll also talk about some important qualitative aspects of cell potentials. The cell potential is it's measured in volts, and it represents the maximum potential energy difference between electrodes, between the electrodes of a voltaic cell. So you can think of this as the driving force behind moving electrons around an electrochemical circuit. And so the idea here is that the electric charge is spontaneously going to flow from high electric potential to low electric potential, and the cell potential is essentially the difference between the electric potential at the two different electrodes. And so you can calculate the cell potential in this fashion. You would imagine writing the reduction potential at the cathode plus the oxidation potential at the anode. And so these represent the potentials at the different electrodes. And you simply add them together to give you the cell potential for the entire electrochemical cell. Now, it turns out that the potential at the cathode, or I should say a reduction potential, is equal and opposite to a reduction potential. And so when you go and you use an electrochemical table to look up electrode potentials, you're not going to find the oxidation potential listed for any particular anodes. However, you will find reduction potentials. And so reduction potentials are tabulated, but oxidation potentials are not. And so what we do is, instead of writing the cell potential in terms of the oxidation potential at the anode, we instead write it as minus the reduction potential for the anode. And that's because the oxidation potential is equal to and opposite the reduction potential. That oxidation potential, it represents the ability of a given anode to give up its electrons, and the reduction potential represents the ability of the cathode to accept electrons. And so the larger these values are, the larger and more positive these values are, the greater the cell potential, the more driving force there is behind moving the electrons around the circuit. When the cell potential is positive, that means you have a spontaneous redox reaction in the forward direction, and it's just going to generate electrical current on its own as soon as you hook the circuit up. If you had a negative cell potential, that would mean that the reaction as written is non-spontaneous, and so it won't drive electrons around the circuit. These cell potentials, they depend upon the experimental conditions of the redox reaction. And so we have what is called the standard state potentials that are evaluated for a specific set of conditions, and then these standard state potentials are then tabulated in various tables. And so for redox reactions, standard state implies that all solutes are present at 1 molar concentration, and then the gases that might be present are at 1 atmosphere pressure, and the temperature needs to be specified, and it's usually taken to be 25 degrees Celsius. When we're at standard state, we label our cell potential with a little superscript circle. This means that cell potential is determined for standard state conditions. In our tables of electrochemical quantities, what you're going to find listed are the standard reduction potentials for different types of electrodes. And so this E circle here, this is a number that you would look up in a table for your cathode, and then you would look up this number for your anode, and then you would use that to calculate the cell potential for the overall redox process. Okay, and so this is something that you need to be able to work with I suggest, in order to help you remember this formula, you use cathode minus anode. Okay, and so you just look these numbers up in the tables and then you use them. You don't have to worry about stoichiometric coefficients. You don't have to change any signs. You just look up the number for your cathode and the number for your anode, take the difference, and that gives you the cell potential. Here I have a diagram here illustrating how the hydrogen electrode works. It's called the standard hydrogen electrode because all other electrode potentials are measured relative to this one. Okay, so this is used to determine the electrode potentials for every other possible anode that you might have. It consists of a piece of platinum metal dipped into a solution containing an acid at 1 molar concentration. You've got here a set of this glass vessel is used to either to pump in hydrogen gas, which is at a pressure of 1 atmosphere, and then it can bubble out through the solution in this fashion. And so you can use the hydrogen electron, the hydrogen electrode as an anode, in which case you have the hydrogen gas being oxidized to H+. Or you can also use it as a cathode, where the acid in the solution is reduced to hydrogen gas. So it can be used either way. In this problem, we are given a description of a galvanic cell. It consists of a gold electrode and a nickel electrode, and we're being asked to figure out which one is the cathode and which one is the anode, and then they want us to write down the half-cell reactions and identify which species is the oxidizing agent and which one is the reducing agent. And so here what I'm suggesting, in order to determine which of these electrodes is the cathode, you just do the calculation each way. So in this first calculation, we'll say, well, let's just assume that gold is the cathode. Okay, and so we'll look up the values of the reduction potentials in a table, and we'll calculate the cell potential for this electrochemical cell. So we'll take the cathode, which in this case we'll assume to be gold, and we'll subtract that from the anode, which is the nickel in this assumption. So you take the cathode number minus the anode number, and we get a positive voltage. If you do this the other way, that is, if you assume instead that gold is the anode and take the nickel to be the cathode, you get the opposite sign, a negative value. And one of the rules that we looked at just a little while ago was that for the spontaneous chemical reactions, the cell potential will be positive. And so this is the correct way to think about these two electrodes. The gold is the cathode and the nickel is the anode. Well, from there you can write down the half reactions. They're right here. And you see that you would need to multiply this half reaction by 3 and this half reaction by 2 before you recombine them. And that's going to give you the balanced redox reaction. Which species is the oxidizing agent? Which one's the reducing agent? I always just remember that the oxidizing agent is reduced. So then I figure out which species is being reduced. We see that the gold-3 ion is being reduced to gold, and so the gold-3 is the oxidizing agent. The nickel is being reduced, so that makes it the reducing agent. Here we're going to talk a little bit about oxidizing agents and reducing agents in some conceptual detail. What I've listed here in the table is it's basically what all of these reduction tables look like. Okay, and so here's the generic form of the reduction reactions in your table of electrochemical reduction potentials. So on the left is always an oxidizing agent, and there'll be some number of electrons that are being gained. And then on the right is the reducing agent. Okay, so in your table you're going to see reactions that look like this. There'll be a whole bunch of them. And then listed next to those are the reduction potentials for these particular half reactions. And you see that some of them are negative, some of them are positive. Here's how we can interpret those values. So certain compounds like fluorine, they really, really want electrons. Okay, so fluorine can basically rip the electrons off of anything. Lithium metal, on the other hand, really wants to give away its electrons. So it would much rather be in the lithium plus species. And so we can use these numbers to establish, or to compare rather, two oxidizing agents to one another, or to compare two reducing agents to one another. And so here are the rules. Okay, the first rule applies to the oxidizing agents, which are on the left side of the half reactions. And the rule is that strong oxidizing agents have very large positive values for the reduction potential. Okay, and so fluorine is going to be the strongest oxidizing agent. Okay, the oxidizing agent is reduced because it wants electrons, right? So the value here indicates that fluorine is much stronger at oxidizing than any of the other species in the table. Conversely, on the other side of the reactions, when you're looking at different reducing agents want to give away their electrons. They want to go in the opposite direction. And so that's the negative sign. So very strong reducing agents have large negative values for the reduction potential. And so we're going to work a couple of examples where we consider these two rules. And then there's a third rule here, that the spontaneity of a redox reaction can be predicted by comparing the strength of either the oxidizing agents or the reducing agents in the reaction. On each side of a redox reaction, you're going to find an oxidizing agent and a reducing agent. So there'll be a pair on each side. The side that has the stronger oxidizing agent is going to be your reactants as far as the spontaneous direction of change goes. And so we'll apply that rule in a bit as well. Okay, so here we've got a list of oxidizing agents: chlorine, peroxide, iron 3, and we are being asked to rank these in order of increasing strength under standard state conditions. So we want to look and find these guys in their find their different half reactions. And so the oxidizing agents are all on the left. And so here we've got peroxide, value of 1.78. We've got chlorine right here, 1.36. And then the iron 3, there's actually two values for that. One is negative, the other is positive. We'll look at the positive one, and we see that it's 0.77. And the rule for oxidizing agents is that the stronger oxidizing agent has a larger positive value for the reduction potential. These oxidizing agents, they very much want to be reduced, and the larger the value, the stronger the reaction in some sense. And so the iron 3 is going to be the weakest of them. The chlorine is in the middle, and the strongest oxidizing agent is going to be the hydrogen peroxide. On the follow-up problem, we're considering different reducing agents: hydrogen, aluminum, and copper. The reducing agents appear on the right-hand side of the reduction reactions. And you're looking for, when you want to talk about a strong reducing agent, you want a species that has a large negative value for the reduction potential. So again, finding hydrogen's over here, it's 0. Aluminum, negative 1.66. And then for the copper, we've got 0.34. Okay, so the largest negative value is for the aluminum. Okay, so the aluminum is going to be the strongest. The hydrogen is in the middle, and the copper has this positive value and so it would be the weakest of those reducing agents. This problem is somewhat similar. So we've got this reaction, and we're being asked, does the reaction proceed spontaneously as written? And so we can do that in a number of ways. One way you can do that is to calculate the cell potential. And if you find out that the cell potential is negative, then that would indicate that the reaction is non-spontaneous in the forward direction. Another way you can do it is conceptually by just comparing the strength of the different oxidizing agents and reducing agents in the reaction. Here we're going to focus on the oxidizing agents. And so the oxidizing agents are on the left-hand side of the half reactions. And the stronger of the two oxidizing agents, notice that we've got one here on the left, and then the iron 3 is on the right-hand side. So there's an oxidizing agent on the product side, and there's an oxidizing agent on the reactant side. Now, whichever one of these is stronger indicates which direction the reaction needs to go. So the rule is that the stronger oxidizing agent is always the reactant. So in this case, we're comparing zinc to iron 3, and we see that the zinc has a negative value, but the iron 3 has a positive value. And the rule is that for oxidizing agents, you want a large positive value for the reduction potential. And so that indicates, since the iron 3 is on the product side, that indicates that this reaction should go towards the reactants here. It should actually go that direction. So that the answer is the spontaneous direction is towards the reactants. Well, I'm going to go ahead and stop this video right here.